All right. So in the last segment, we saw our forms of the balance of linear and angular momenta for deformable bodies, right? And we saw that this was possible once we admitted the notion of a stress tensor, right? And we saw how the stress tensor shows up in the equations. We also saw that if we assume that the stress tensor is symmetric, then the balance of angular momentum is automatically satisfied. For the type of mechanics that we're studying in this series of lectures, we are not considering additional effects that would render sigma non-symmetric, that would render the Cauchy stress non-symmetric, and therefore the balance of angular momentum is automatically satisfied. Okay? So what we're going to do in this segment is just look at a couple of properties, if you will, of the stress tensor. All right? So let's look first at, let's look at the idea of the normal and shear stresses on a surface. Well, let's look at the normal and shear tractions actually on a surface. Okay, so here's the setting. Current configuration. Now I am going to consider the general case of an internal surface, right? And remember that we can always define this mathematically, right? So this is my internal surface gamma. Everything I develop for this is equivalently applicable to the external surface of the body as well. Okay? All right. Let's suppose then that this is the normal. Okay? And if that is the normal, and that's the stress sigma, we have across this surface, we have a traction vector, T. Right? And we know the relation now, sigma n equals T, okay, on the surface gamma, which is a subset of our current configuration of the body. All right, we have the situation. What I want to consider are two really easy concepts. The first is, what is the normal component of the traction vector? Okay, that's actually trivial to do here, right? So the normal traction okay. The normal traction, of course, is just n dotted with T, right? That's the scalar value of the normal component of the traction. But then we want to write it as a vector, so we multiply it again with n. Okay? Right? The way this can be applied to T is the following. Invoking the idea of our tensor product or the dyadic product, we have n tensor n as a second order tensor acting on T. Right? And you see how this works, right? Because because the second n, the n on the right hand side in that tensor product is dotted with T, and that's multiplied by n, right? That's in fact the definition of the tensor product. Okay, but then many units ago we had introduced this when we were studying the dyadic product or the tensor product, and we noted that this was actually what we call a projection tensor, and we denoted it as P sub n. Okay? So we observe that the normal component of the traction can be obtained by this projection tensor acting on T. Okay? Right? All right. Let's go on then and look at the shear traction. Well, the shear traction is just that part of the traction that is not the normal traction, right? Because essentially what we've just computed up here is the idea of, let me see, I'm going to draw it here, but at the risk of going through that n, let me move the n to the side. Okay, and now if we extend this just a little, this second vector, so this n is that vector, the second vector is essentially Pn acting on T. Okay, that's a normal component. Okay, it's meant to be, well, you know how it is, it turned out to be a little longer than it should have been. Okay, so the shear traction essentially is this component then. Okay, that is the shear traction. All right, so that is T minus Pn acting on T. But this we can write as 1 or a second order isotropic tensor minus this projection tensor acting on T. But this is what we called, this is also a projection tensor. Okay, and I remember now that when we originally defined the normal projection tensor, we'd called it P perp, right? Instead of n, we'd use the perpendicular symbol, but it's essentially the same thing here. Let me just use PS here. Okay? All right. So this then is PS acting on T. Okay, that's the shear traction. So PS actually, if you go ahead and we could always write it out in this form, right? 1 minus n tensor n. Second order isotropic tensor minus n tensor n. Okay? Recall, right, these results. Pn acting on Pn equals Pn. PS acting on PS is also PS, right? They're both, right? And these properties together, or actually even taken separately, each of these projection tensors has the property of idempotence. Okay? All right? And then we also have this condition that Pn PS equals the zero tensor. Okay, so those two projections are essentially orthogonal projections, right? So this is orthogonal. Okay. All right. So that's what we have then for how we can think of the traction along any surface as being decomposed into a normal and shear component. Okay. All right. The next thing I want to do is the following. So now we've introduced this idea of the normal component of the traction, and we see that if we look at the scalar value of that normal component of the traction, okay, so note that the magnitude of the normal component of the traction is n dotted with t, okay, which just comes from the result we had in the results we had in the previous slide, which of course is just n dot sigma n. Okay. So this means that you take some, you take any direction n, you form that quadratic product with sigma, and it gives you the normal component of the traction in the direction n. All right. So let me call this also. Let me say that this is the normal component of, really it's the magnitude of the normal component of the traction, along n. Okay. Now this is also often referred to actually as the normal stress along n. Okay. Okay, this thing's also called, for obvious reasons, right? It's also called the normal stress along n. Okay. Now, once we have this, it's a reasonable question to ask that, okay, now as I change n, how do I know, it would be of interest to me to know along what direction of n I get the maximum stress. Okay, because clearly that can have applications in how you view the maybe the failure of this material eventually. Right, so you expect that if the stresses are maximum along some direction, then the material is probably going to fail along those directions due to fracture or something like that. Okay, so the question we want to ask is, more generally, how do we find the extrema or the extremum values of the normal stress, right? N dot sigma n. Okay. Now, the way we find maxima and minima or extrema in general is through this differential condition, right? The condition for first order extrema, right? So, essentially the approach is the following, right? Right? So we consider the following, right? We want to consider the derivative with respect to n of that quadratic product, n dot sigma n. Okay? Except that this is not quite enough, because if we just go ahead and compute this, we need to also impose the requirement that n is a direction. Right, and that n has unit magnitude. If not, as you can imagine, you pick any direction n and just make n big enough, right? You just keep increasing n, and this quantity is going to be unbounded, right? We really want to know we want to know something about sigma, and we don't want to have the magnitude of n affect the result. Okay, so what we need to do is impose the constraint that n has unit magnitude. And the way this is done is using Lagrange multipliers, or one way to do it is using Lagrange multipliers, which impose the condition that n dot n minus 1 is equal to 0, right? So if you want to impose the condition that n has unit magnitude, right, we add on a Lagrange multiplier term of this type, where lambda is the Lagrange multiplier. Okay? So the idea is that we take this entire function now, and what we do is, rather than compute the derivative with respect to n only of the first term, okay, what we do is we construct a different functional. Okay, so what I'm going to do here is actually rewrite this, because okay, so the approach is that we okay, I'm going to get rid of this stuff here, okay, because I use that only to sort of make the argument about how we can construct extrema, but we're not going to actually do exactly that. Instead, what we're going to do is we consider this function. Okay, so consider this function. So consider this function of n and lambda, okay, where lambda is the Lagrange multiplier. Okay, right? So let's suppose that we have this function. Let's write it as pi. It depends upon a direction n and the Lagrange multiplier lambda, and it is n dot sigma n minus lambda times n dot n minus 1. Okay, and the idea here is that this is the constraint. Okay, so what this does is, the constraint is that it imposes a constraint on magnitude of n. Okay, and now we consider the extremum problem with respect to n and lambda. Okay, so what we do is we say that, all right, we want to have partial of pi with respect to n equals 0. Okay, which implies that we're going to calculate that, but then let's do it in coordinate notation. Okay, so what we're going to do is partial of pi with respect to n k ek equals 0. Okay, and as we've done before, we can choose to work only in terms of the initial quantities. Okay, for that purpose, let's first rewrite pi as ni sigma ij nj minus lambda nl nl minus 1. Okay, and then we are going to consider partial of pi with respect to nk. Okay, when we do this, we get the following, right? We get delta ik sigma ij nj plus ni sigma ij delta jk minus lambda, right, or twice lambda delta lk nl. Okay, just using the fact that the derivative of any n with some index with respect to n gives us a Kronecker delta in those two indices, right? Okay, now we can rearrange this observing that we have, okay, so in this case we can apply the Kronecker delta to the sigma, and that reduces the sigma in from the first term to sigma kj nj. For the second term, it reduces that product to ni sigma ik, and the last term comes along for the ride. Well, it doesn't come along for the ride. There, the Kronecker delta converts the index on n to a k. Okay, that's the condition we need. All right. Now, sigma is symmetric, right? So the first two terms can be written as sigma kj nj, which is the first term, no change there. But here I'm going to write this as sigma ki ni minus 2 lambda nk equals 0. Okay, sorry. These are implication signs, right? Okay. Now, in the second term, we can view I, well, in the first two terms, j and I are just dummy indices because they're being contracted away. Okay, so those first two terms are really the same since sigma is symmetric, right? Since sigma ik equals sigma ki. All right, that's what allowed us to write this very last equation. Okay, but now since I and j are just dummy indices, we can always rewrite this as 2 times sigma kj nj minus 2 lambda nk equals 0. Okay? Right? So this is the first condition. The second condition is partial of pi with respect to lambda equals 0, which, recalling what pi is at the top of the slide, gives us essentially NL minus 1 equals 0, which essentially imposes the magnitude condition. Okay, it imposes the constraint. Now, so in direct notation, okay, what we have is, of course, we can get rid of the 2's here, right? If you write that first, the second last equation on this slide, you rewrite it in direct notation, you see that what we have is sigma n equals lambda n, okay? And the other condition is that the magnitude of n square equals 1, or the magnitude of n equals 1, right? Okay, do you recognize that condition? That is our statement of a standard eigenvalue problem on the stress. Okay? This condition is our standard eigenvalue problem for sigma. Okay? I'll write it here again. So our condition is sigma n equals lambda n, where n is a direction. Okay? So in this in the eigenvalue, in the standard eigenvalue problem, lambda are the eigenvalues, okay, which you have otherwise heard in the context of the stress as being the principal stresses. Okay? And n is the corresponding eigenvalue. Okay? What this demonstration has shown for us is why it is that the eigenvalue problem, the standard eigenvalue problem, needs to be solved in order to find the maximum or minimum normal stresses. Right? We know that, right? We know that among the solutions of the eigenvalue problem arise the maximum and minimum stresses along any given direction in the body, right? Given the stress tensor, right? This little demonstration using this idea of finding extrema with the constraint imposed using the Lagrange multiplier tells us why that is the case. Okay? And we also understand that the role of the Lagrange multiplier here is essentially it is in fact the eigenvalue. Okay? So whenever you solve a problem with a constraint using a Lagrange multiplier, you need to solve for the Lagrange multiplier. And in this case, we view the Lagrange multiplier as being that sort of component of the stress which is imposing the condition, right, that the direction have unit magnitude. Okay? Just a couple of more properties which follow from the fact that the stress is symmetric. Sigma equals sigma transpose implies that lambdas are real. Okay? Since the lambdas are real, okay, it's always possible to set, okay, the eigenvectors, okay, n has 3 values corresponding to lambda equals lambda 1, lambda 2, lambda 3. Okay? And the values n1, n2, n3 can be made to form an orthonormal set. Okay? Okay? Oh, I realized that hopefully I said eigenvector out here, but I also wrote eigenvalue again, so I'll just correct that. N is the eigenvector. Okay? Eigenvectors, because there are 3 of them since we're working with the stress in 3 dimensions. Okay, that sort of sums up what I wanted to say about the properties of the stress tensor, properties of the traction vector and the stress tensor, and we can stop here for this segment.